I'm Randolph Klein, one of the great instrument scientists, together with Simon and Kyle. And I'm going to present here an example for grade, in this case mapping the Horsehead Nebula. But before going into the details of that, here a quick overview over the grade capabilities. You have, let me switch on that red pointer, basically three receivers. HFA, high frequency, LFA with both polarizations, or LFA stands for low frequency array. And then there is 4-grade, which offers 4 different receivers in one package. Note that we can fly 2 receivers at a time, but only the following configurations: LFA and HFA, or 4-grade and HFA. So you always hit the HFA with one line on a given flight, and you need to choose kind of want to pair it with the LFA or the 4-grade. Your proposal can include all receivers, but for a given flight, you have only kind of one of these 2 configurations. Now, this is probably mostly driven by your science, which one you choose. Now, for map types and observing modes, there are more choices, and I want to quickly go over them. First, there is single point. That's pretty much self-explanatory, just one pointing, that's it. A raster map is basically single pointings in a regular rectangular grid. That's mostly applicable for small, deep maps. If you don't kind of want a rectangular raster, you have to do several single pointings as a separate thing. More efficient are the OTF maps. For small maps, we recommend the new OTF Honeycomb Map. Small in this case means the size of the array. The HFA and LFA consist both of 7 pixels, and so where I'm talking about the array size is the configuration of the 7 pixels. Look up the actual size in the handbook. When your target area, your mapping area is larger than a few arrays, then you want to go to one of the OTF maps, the classical on-the-fly map, classical OTF, which is good for large, deep maps, meaning kind of faint targets. You have a kind of rather bright one where you don't need a lot of time per point. The OTF array map is more efficient. Now, any of these modes can be combined to do the background subtraction with either beam switching or total power. Total power is when you move the telescope to a reference position. It can be far off, so that's the typical mode you use for large maps, because you're mapping a large area because the source is extended, and though thus your reference position, which has to be free of emission, has to be far away, and then total power is the only way to go. It also works very efficient with OTF maps. If your source is more compact and your reference position can be closer by, you can use the much faster switching method with the secondary mirror, which is chopping. That's then called beam switching in grade terminology. This requires, though, a much closer reference position, thus only usable for point and compact sources, but it offers better sky cancellation baseline stability, which may be important if you're looking for weak and or bright broad lines. So yeah, here are just some reference pictures for the, going back now to the mapping modes here. You can find these in the Observings Handbook so that you can easily find the sections where you can find more details about all these mapping modes. The classical OTF map, array OTF map, where you just do less stripes than in the classical one, or the nice honeycomb or snowflake mode. Name comes, yeah, obvious why it's named like this, I think. So just look it up in the handbook. This is also the most important slide here in the whole presentation I have here. Look up the details in the Cycle 9 Observer's Handbook. It contains more examples than I'm presenting here, and more details on these mapping modes, for example. And if you have any questions about that, ask us early at our help desk email. ask them early so that we can research the answer, give it back to you so that you have time to still work it into your proposal, and then you can ensure that your proposal doesn't die in the technical review. So now into the example that I want to kind of work with you through here. Let's suppose we want to observe the iconic Horsehead Nebula in the C+ line at a high spectral resolution. By that I mean 1 kilometer per second. And we want to kind of map this fairly well, this area, 12 arc minutes by 17 arc minutes in size, slightly slanted so that we get the PDR, kind of the transition between the ionized region and the molecular cloud, nicely in the map and encompass the whole Horsehead Nebula here. This is kind of a trunk like the pillars of creation like structure in this sticking out of the PDR interface. Wavelength C+ line requires gray or FIFLS. The spectral resolution here requires a spectral resolution of grade, and thus this example. Now, we need first an idea kind of how bright is the line. I took here an example which might be very applicable to your source. You might find a PAX Herschel observation for your source. Here I just quickly went to the postcard, postage stamp server, I think it's called. You can quickly grab here a line. It's not good for science, but for a rough flux estimate should be good enough. PAX doesn't resolve the line. It measured here unresolved line width of 0.14 micron. You can convert that to frequency space. The peak flux here is 65 Jansky per PAX spaxel. You can convert that to per arc second, square arc seconds. But we eventually need to convert it to the C+ beam, kind of how much flux would be in SOFIA's beam at the C+ wavelength. Grade measures its beam width here at 14.1 arc seconds, full width half maximum. So that converts roughly to 110 Jansky per beam. Now, the intrinsic line, which is much smaller than PAX measured, we have to assume an intrinsic line width of 10 kilometers per second here. Well, that's kind of my choice. And therefore, the intrinsic peak flux density boosts up to 0.9 kilojansky per beam. Since grade is a heterodyne instrument, it doesn't do Janskys, but it works on a temperature scale. So you have to convert the Janskys, kilojanskys, to antenna temperature. The equation for that and the way how to derive that equation, if you're interested, is in the observer's handbook. It's basically just divided by a little factor of less than 1,000, but you're on this order of accuracy. The antenna temperature comes out to 2.9 Kelvin roughly. So that is the value that we need in sight to estimate the observing duration, the integration time. Here with screenshot of the time estimator, I go through with you kind of how to enter. What to enter. First, we of course need to specify the rest frequency. It's pre-filled with a C+ line because that's a line. And if you want to have a different line, look up the exact frequency in Catalog or your favorite line catalog online. You need to specify the frequency or velocity resolution. Here, 1 kilometer per second. That's very important. The estimate depends very much on this value. You also enter the expected line width. Here, 10 kilometers per second. The result doesn't depend very much on this value. Now, this is kind of a very bright line, and we want to extend, mapping a large extended area. So we are going for total power, because the off position has to be far away. And so we select here total power OTF. The map size in arc seconds is this. Leave the next field n on empty because site will suggest a value of n on. N on is how many on positions you observe before you go to an off position. That makes these OTF maps so efficient that you don't do an off for every on, but only after so many, and then you spend a little bit longer at the on, but in the end you spare a lot of time. I should add that for the Honeycomb mode, as you can read in the handbook, that has 25 positions before it goes to an off typically. So you enter 25 for the Honeycomb, otherwise leave empty. I could have chosen here classical or area OTF. It's bright enough for an area OTF, but since most of your sources are probably not as bright and it works with a classical OTF, I want to work that example with you here as a classical OTF map. Now, your desired signal to noise ratio depends a bit on kind of how you made your flux estimate. You think kind of that's a peak flux, and you probably want to have a high signal to noise ratio. If you went kind of for, that's kind of the RMS noise that you want to get, you probably want to enter desired signal to noise of 1 for this estimated noise level. Here I went with 5, kind of as an average low value, hopefully in my map estimate, flux estimate. So desired signal to noise of 5 for this brightness temperature. Note here that's the brightness temperature, not the antenna temperature. 4 great with its good forward scattering efficiency. That difference is only about 3%. The equation is also in the handbook. If you come, for example, from somewhere else and you have, for example, on the main beam temperature scale, the factor would be something around 0.67 or so. So pay attention to the temperature scale. Here you need to enter the brightness temperature. And you want to have the source velocity for the horse head, that's 10.5 kilometers per second. And then you can hit the calculate button. It's not in this location on the screenshot, but just to show that calculation button. Now, this is what you get, or kind of the important part from that result page. You get first the atmospheric transmission in your observing window. The green line is where you expect the line. And I should remind you that GRADE is a heterodyne instrument and dual sideband receiver, meaning it basically gets 2 sky frequencies at the same time. Signal band, where your line is, and then the image band, but you can choose one of them. The signal band should be the upper or lower sideband, and then you get basically noise from the other one, and so that will be either the blue or the red location. Here, the sky is equally transparent, meaning also equally emissive at these, so there is not a big difference in this case, but there can be a big difference. Now, the important...
Randolph, you have about 10 minutes.
Thank you. But the important output numbers are N on 85, that's kind of what we left open, and the integration time on source per point 3.8 seconds. Now, what does N on mean? I want to go through that a little bit. The default map spacing for LFA is 6 arc seconds. With 85 on positions, the scan length is 510 arc seconds, which you will notice is half the map size. So SITE is suggesting that we should split the map in half to have a proper scan length. Note that the OTF scan should be shorter than 30 seconds for the LFA, 20 seconds for the HFA. And that's how basically the number was derived. On-source exposure time 30 seconds divided by the number of on-source plus the square root of the on-source positions. That's how long you spend in the off-source. You come to an exposure time per point of 0.3 seconds, and that goes into U-spot. As I said, map layout, we want to kind of scan in this direction, but because we want to stay within 30 seconds of scanning, we only can do half. So in here for actually 4 map areas, this is the off position. You might want to shift it a bit further, but I wanted to have it here on the visualization from U-spot. So with 6 arc second step size, we have 85 by 60 steps, 85 points along the scan direction and 60 basically scan lines. You need some trigonometry to kind of get the offsets for all the 4 quadrants. As I mentioned, we want to scan or have the map layout along the line here, so you can choose actually a map angle that kind of creates this slanted scan direction. There's a magic array angle. This is illustrated here also from the handbook of 19.1 degrees when you turn the array by 19.1 degree, you get each pixel scans then along a line, and all the lines are equidistant. You can see that here in the visualization. I zoom in here, all these pixels kind of match and map edges here are equidistant. And when I kind of designed kind of how the maps attach each other, the fringe kind of there we have tapering off of the exposure time because not all pixels reach there. But if you kind of match them nicely together, that kind of adds up to kind of full coverage here in the overlap region. Now back to the time estimate. In the classical OTF map, all the 7 pixels of the array plus the 2 polarizations for the LFA cover the inner part of the map. If you do the area OTF map, that's kind of the more efficient one. You only get 1 pixel. But now with the classical OTF, 1 coverage per gives you 14 coverages basically, and when you have dwell only 0.3 seconds in one position, or kind of move the telescope so that it stays 0.3 seconds in a 6 arcseconds area, we actually integrate for 14 times that, so 4.2 seconds per map per sky position. And that's about the 3.8 seconds. So 1 coverage in the classical OTF map gives you already all the time that you need. Here, this calculation is done for you. The remainder lines here is done for you in USpot, just kind of so that you have the background. I tell you what's happening there. So you have 85 on positions, then times the 0.3 seconds, then you spend square root of 85 times 0.3 in the off position. You do that for the 60 scan lines, so that gives you 1700 seconds, almost 1700 seconds per AOR, plus an overhead that's also calculated in USpot, meaning 1 AOR is almost an hour, and the 4 map tiles gives you a total time for this map of almost 4 hours. Now you need to put all that into USpot. Here, a quick screenshot of that. Source velocity is important for us, so I only now go first over the entries that you have to make for phase 1. The rest can be solved during phase 2, also in iteration with us. So we don't want to know the source velocity. Obviously, you have to specify the frequencies. HFA frequency is pretty much always the 1 line. Since we're going here for the C+ line, enter the C+ frequency for both polarizations. That's actually new. You can now choose 2 different polarizations, but then of course you get, if you split that, only 7 coverages, kind of 7 pixels per each frequency. Primary frequency is where your science, the most important line in your science, or kind of which of the receivers has the most important science line for you. The mixers specify the configuration that you're going to use. Mixer 1 has to be HFA. In our case, Mixer 2 is the LFA because we want to do the C+ line. As I mentioned, we do this in total power. On-source exposure time was 0.3 seconds. We went through that. And 1 cycle was enough because 0.3 times 14 was 4.2, which was then more than the 3.8 that we estimated. Also, of course, important for the time estimate, and this is what we need in phase 1, are the number of steps in X direction, which in this case is the scan direction, and then the number of steps in the Y direction. So this is the entries for one of the 4 maps. Yeah, you have to kind of enter that 4 times with different map offsets here. But yeah, the important part for phase 1 are only the one with the red stars, so that's it. And now I want to remind you, ask us early on that, with that helpline or now. For example, how much time is remaining? I have
3 minutes.
3 minutes. So I think I stop here. The presentation that you can download has some more screenshots where just highlighting all the areas which are important for the visualization, which let me do this plot here. This is helpful for you to kind of sort out that your observing strategy is right, but we can sort out the details in phase 2, definitely. Yeah, that's it for now. Any questions?
Hi, Randall. Question from Yaolu. Inside, should I use the array size as the map size for honeycomb mapping?
Sorry, can you repeat that? I didn't quite get that.
So inside, what do you use as the array size in honeycomb mapping? Should you use the map size or something different?
If I'm not mistaken, if you put in an on, the map size doesn't matter. Note when, let me go to, let me go to here. The output of site doesn't tell you, for example, how long the whole map takes. It takes only the map size to make an estimate of n on, but if you specify n on, the map size actually doesn't do anything. So for honeycomb map, just put the 25 here and you're good.
Okay, thank you, Randolph.